All right, welcome to another deep dive, everyone. Today we're going to be exploring a topic that was requested by you, our listener. It's all about quadrilaterals, which, honestly, I thought I knew pretty well until I saw the source you sent in.
Yeah, it's really thorough. We're going to try to distill it down into the most important insights for you, our learner. Hopefully, we can bring you some real aha moments about these geometric
Yeah.
shapes.
So the source we're diving into is a document that systematically explains different types of polygons. It gives us definitions, properties, and examples, but it really focuses on quadrilaterals, as you requested.
And those are the four-sided figures that we encounter every day.
Exactly.
Hmm.
But we often overlook the underlying geometry that makes them so interesting.
Right. It's more than just squares and rectangles. There's a whole world of fascinating relationships to uncover.
So let's start at the very beginning. Our source defines a polygon as a simple closed curve made of line segments.
Like if you were to draw a shape without lifting your pen or crossing over any lines.
Exactly. And it can have any number of sides as long as it's closed and made of straight lines.
So a triangle is a polygon, a square, a pentagon, a hexagon, and so on.
Right. Now, the source quickly introduces a key distinction: convex versus concave polygons.
And this might sound a little technical, but it really comes down to whether the shape has any inward dents or bulges.
Okay, can you give an example?
Sure, think of a star shape. That's a concave polygon.
Ah, I see. Because some of its points are pointing inwards.
Right, but if all the points are pointing outward, like in a regular pentagon or hexagon, then it's a convex polygon.
Okay, that makes sense. And the document makes it clear that we're mainly focusing on convex polygons for our exploration today.
Yeah, they're the more common ones, and they make the geometry a bit easier to understand.
So moving on, the source then talks about regular and irregular polygons.
And this is all about how specific rules about sides and angles create different categories of polygons.
Right, so what exactly makes a polygon regular?
A regular polygon has to meet two very specific conditions. It has to be equiangular, meaning all its angles are equal, and it has to be equilateral, meaning all of its sides are equal.
Okay, so a square would be a classic example of a regular polygon.
Exactly. Four equal sides, four 90-degree angles.
But then, the document contrasts that with a rectangle, calling it an irregular polygon.
Right, because while all the angles in a rectangle are also 90 degrees, making it equiangular, its sides don't necessarily have to be equal.
So the lengths can be different from the width.
Precisely. And the source even poses a question to the listener here. Can you think of an equilateral triangle?
Ooh, I like this. It's getting interactive.
Yeah, it's prompting our learner to engage. So is an equilateral triangle where all three sides have the same length also equiangular?
And the answer is yes. All three angles in an equilateral triangle are also equal, each measuring 60 degrees.
Making it both equilateral and equiangular, which means it's a regular polygon.
Exactly. And it's interesting how the document uses little dashes on the sides of the figures to show which segments have equal lengths.
Yeah, it's a nice visual cue that helps us quickly understand the properties of the shape.
All right, with that basic understanding of polygons in place, the document takes a really fascinating turn into exterior angles.
This is where we encounter a rule that's almost like a secret of the geometric universe.
Ooh, I like secrets. Tell me more.
Okay, imagine you're walking along the edge of any polygon. When you reach a corner, you have to make a turn to continue walking on the next side, right?
Right.
Now, if you keep doing this, walking along each side and turning at each corner until you're back where you started, you'll have made one complete turn.
Okay, so you've essentially gone in a full circle.
Exactly. And here's the incredible part. The total amount you turned at all those corners, the sum of those exterior angles, will always add up to exactly 360 degrees, no matter what polygon you're walking around.
Wow, that's pretty amazing. Doesn't matter how many sides the polygon has.
Nope. It's a universal rule. The sum of the exterior angles of any polygon is always 360 degrees.
That's a really elegant concept, and the document gives a simple example to illustrate this, right?
Yeah, they show a four-sided shape, and they tell us three of its exterior angles are 90 degrees, 50 degrees, and 110 degrees.
So to find the missing exterior angle, which is labeled x, you just set up an equation. X plus 90 plus 50 plus 110 equals 360.
And solving 4x gives you 110 degrees.
It's like a puzzle where you always know the final answer has to be 360.
Exactly. And then the source takes a step further and explores a regular hexagon.
Okay, a six-sided shape where all the sides and angles are equal.
Right. And it poses some insightful questions. What's the total of its exterior angles?
Well, we know it has to be 360 degrees because that's the rule for any polygon.
Right. Are all the exterior angles in a regular hexagon equal?
Well, since it's a regular hexagon, meaning all its angles and sides are equal, then the exterior angles must also be equal,
Exactly. And then, to find the measure of each exterior angle, you simply divide the total, 360 degrees, by the number of angles, which is 6.
which gives us 60 degrees for each exterior angle of a regular hexagon.
And the source even extends this idea to regular octagons, which have 8 sides, and 20 gons, which have, well, 20 sides.
Just reinforcing that no matter how many sides a regular polygon has, the sum of its exterior angles is still 360 degrees, and all the exterior angles are equal.
And it gets even more powerful. Example 2 shows how you can use this concept to work backwards.
What do you mean?
Well, if you know that each exterior angle of a regular polygon measures 45 degrees, you can figure out how many sides it has.
Wow.
You simply take the total, 360 degrees, and divide it by the measure of each exterior angle, 45 degrees.
So 360 divided by 45 gives you 8, which means that polygon must have 8 sides. It's an octagon.
Exactly.
That's so cool. I'm starting to see how these seemingly simple concepts can unlock a lot of information about these shapes.
Absolutely. And exercise 3.2 in the document really reinforces all of this. It has you calculate missing exterior angles, determine the measure of each exterior angle in various regular polygons, and find the number of sides when you're given an exterior angle.
So like a good workout for our geometry muscles.
Definitely. And it even challenges you to think about whether a regular polygon can have a certain exterior or interior angle measure at all.
For example.
Like, could a regular polygon have an exterior angle of 22 degrees?
How would we figure that out?
Well, remember, the sum of all exterior angles has to be 360. So you would need to check if 360 is perfectly divisible by 22.
Right. If it's not, then you can't have a regular polygon with that exterior angle measure.
Exactly. And the exercise even explores the limits, like what's the smallest possible interior angle and the largest possible exterior angle you can have in a regular polygon.
I wonder how that works.
Well, think about it this way. As you add more and more sides to a regular polygon, it starts to look more and more like a circle.
Oh, I see.
Right. The exterior angles get smaller and smaller, approaching 0, while the interior angles get closer and closer to 180 degrees.
Makes sense.
Yes.
So the smallest possible interior angle for a regular polygon is 60 degrees, which is what we see in an equilateral triangle.
Which then corresponds to the largest possible exterior angle of 120 degrees, because those two angles have to add up to 180 degrees.
Right. Okay, so this exploration of exterior angles gives us a really powerful way to understand and analyze polygons in general. But now, the document shifts gears and really dives into what many of us think of when we hear geometry, the different kinds of quadrilaterals.
This is where we start to see that fascinating family tree of four-sided shapes emerge.
I'm excited to see how they all relate to each other. So where do we begin?
At the base of this quadrilateral family tree, we find the trapezium, or as it's sometimes called, the trapezoid.
Right, and its defining characteristic is pretty simple.
It's a quadrilateral with at least one pair of parallel sides.
Parallel sides, meaning those sides will never intersect no matter how far you extend them.
Precisely. And often you'll see these parallel sides indicated with little arrows and diagrams to make it clear.
Yeah, like in the figures in the source document.
Exactly. And what's really interesting is that the source encourages a hands-on activity here using congruent triangles and set squares to actually create trapeziums.
Help like a way to visualize it.
Right. It also helps us understand that the non-parallel sides don't have to be the same length.
But they could be, right.
Yeah, and that's where we get a special type of trapezium called an isosceles trapezium. It has those non-parallel sides of equal length. And because of that equal length, it also gains a line of symmetry.
Okay, that makes sense. So we have the trapezium at the base of our quadrilateral family tree. What comes next?
Next up is the kite, which has a very specific definition.
Lay it on me.
A kite has exactly two distinct consecutive pairs of sides that are equal in length.
So like a classic kite you'd fly, where the two shorter sides next to each other are the same length, and the two longer sides are the same length, but the shorter pair is different from the longer pair.
Exactly. And the document suggests a really neat paper folding activity to illustrate this.
Oh, I love a good paper folding activity.
Right. It makes the geometry so much more tangible. So you fold a piece of paper in half and then cut out two connected segments of different lengths from the folded edge. When you unfold it, you get that classic kite shape.
I see it. It makes sense why it's called a kite. Now, the source goes on to explore some key properties of kites, And it does this through additional paper folding or by just careful observation of the shape,
Yeah, and some really cool things emerge. First, there's the line of symmetry right down the middle.
which means you could fold it in half along that line and both sides would perfectly match.
Exactly. Then there's the fact that its diagonals, those lines connecting opposite corners, are perpendicular to each other.
So they meet at a 90-degree angle.
Precisely. And then there's the fact that one diagonal bisects the other, meaning it cuts it in half.
And usually the longer diagonal bisects the shorter one.
Right. And that longer diagonal also bisects the angles at its two ends.
Wow, so many interesting properties packed into one shape. Now, this makes me wonder, and it might be a bit of a trick question, but is a square a kite?
Ooh, that's a good one. It's tempting to say yes, because a square does have four sides, and all of them are equal in length.
So it definitely has two consecutive pairs of sides that are equal.
Right. But the definition of a kite specifies exactly two distinct consecutive pairs of sides of equal length.
So the distinct part is key here.
Yeah, and that's where it gets a little tricky. A square does have four sides of equal length, but it doesn't have only two pairs of distinct consecutive equal sides.
So does it technically qualify as a kite?
It depends on how strictly you interpret the definition.
This is a great example of how precise geometric definitions can be. Sometimes it's not so black and white.
Absolutely. But in many mathematical contexts, a square is considered a special type of kite.
Okay, that's good to know. All right, let's move on to the next quadrilateral in our family tree. What's next?
The parallelogram. And as the name suggests, this shape is all about parallel lines.
And the document provides a great activity to visualize this, using rectangular strips of cardboard.
Yeah, by holding those strips together and moving them around, you can see how a parallelogram is formed by two pairs of parallel lines.
And the definition is pretty straightforward, too.
A parallelogram is a quadrilateral where both pairs of opposite sides are parallel.
So if you extend those opposite sides forever, they'll never meet.
Precisely. And from that one fundamental property flows a whole set of other interesting characteristics.
Like,
Well, for starters, the document emphasizes early on that opposite sides of a parallelogram are always of equal length.
okay, so not just parallel, but also equal in length.
Exactly. And this can be proven either through careful measurement or through a more formal geometric proof using congruent triangles.
And the source shows us how this property is actually very useful in example 3, right?
Yeah, because if you know the lengths of two adjacent sides of a parallelogram, you immediately know the lengths of the other two sides.
Which makes calculating its perimeter, the total length of all its sides, super easy.
Exactly. Then the document dives into the angles within a parallelogram.
Okay, so now we're looking at the relationship between those parallel lines and the angles they create.
Right. And the source uses some really clever methods to demonstrate that opposite angles in a parallelogram are always equal.
Like what?
One way is by using tracing paper and rotating the parallelogram to show how those opposite angles line up perfectly.
Ah, so it's a visual way to prove the concept.
Right. But you can also understand this through the geometry of parallel lines cut by a transversal.
Okay, remind me what a transversal is.
A transversal is simply a line that intersects two or more parallel lines.
Right, okay.
And when that happens, it creates special angle pairs, like alternate interior angles, that are always equal.
And that directly translates to the opposite angles of a parallelogram being equal.
Precisely. Example 4 in the source shows how you can use this property, along with the fact that angles on a straight line add up to 180 degrees, to figure out unknown angles in a parallelogram.
So we can solve for those missing angles using logic and the properties of parallel lines.
Exactly. Then the document takes this a step further and shows us that adjacent angles in a parallelogram are supplementary.
You mean?
They always add up to 180 degrees.
Okay, so not equal, but they sum to 180.
Right. And this property also comes straight from the rules of parallel lines and transversals. When you have parallel lines cut by a transversal, those consecutive interior angles on the same side of the transversal are always supplementary.
So in a parallelogram, those consecutive interior angles become the adjacent angles, and they must add up to 180 degrees.
Precisely. And example 5 demonstrates this beautifully. It shows how if you know just one angle in a parallelogram, you can use both the opposite angle property and the supplementary adjacent angle property to figure out all the other angles.
Ah, so we can unlock the entire angle situation with just one piece of information.
Exactly. And finally, the source wraps up its exploration of parallelograms by looking at their diagonals.
Diagonals, the lines connecting opposite corners.
Right. And it starts with a simple paper folding activity to help visualize that the diagonals of a parallelogram always bisect each other,
I mean,
meaning they cut each other in half at their point of intersection.
so the point where the diagonals meet is the midpoint of each diagonal.
Exactly. And this property, like many others we've seen, can be formally proven using congruent triangles. But the paper folding gives a really nice visual demonstration.
Definitely. And the source gives a practical application of this concept in example 6. Right.
Yeah. Yes. It shows how if you know the length of part of one diagonal and maybe some relationship between the lengths of the two diagonals, you can use the fact that they bisect each other to solve for unknown lengths.
Clever. So we've now explored a bunch of properties of parallelograms, but the document doesn't stop there, does it?
Nope, it keeps going. We still got exercise 3.3 to cover. This exercise is like a knowledge check for all things parallelograms.
Ooh, like a pop quiz.
Kinda. It has all sorts of questions to really make sure you understand the properties we've just discussed. You have to fill in missing parts of statements about parallelograms, calculate unknown angles and side lengths from diagrams, and even think about what conditions are absolutely necessary for any quadrilateral to be classified as a parallelogram.
Sounds comprehensive.
It is. And there's this one really interesting question about a quadrilateral that's not a parallelogram but still has two opposite angles equal.
Which shape could that be?
Remember earlier when we were talking about isosceles trapeziums?
Oh, right. They have those two opposite angles that are equal, but their sides aren't all parallel.
Exactly. So they fit the description. And there's even a question about the ratio of adjacent angles in a parallelogram, which you can solve using the supplementary property we learned about.
So much to explore just within the realm of parallelograms. But now, the document takes us to the next level. Special parallelograms.
These are parallelograms with additional specific properties that make them even more interesting.
Okay, I'm intrigued. Where do we start?
We start with the rhombus, which is actually cleverly introduced by connecting it back to the kite.
Okay, how so?
Well, the source describes a rhombus as a kite that happens to have all four of its sides equal in length.
Ah, so it has that kite-like shape, but with the added condition that all four sides are the same.
Precisely. And since it has opposite sides of equal length, it automatically qualifies as a parallelogram too. So it inherits all those parallelogram properties we just talked about.
So it's a parallelogram and a kite.
Exactly, a double whammy. But what makes the rhombus really stand out is what happens with its diagonals.
Those lines connecting opposite corners.
Right. The document highlights that the diagonals of a rhombus are perpendicular bisectors of each other.
So they're perpendicular, meaning they meet at a 90-degree angle, and they bisect each other, meaning they cut each other in half.
Precisely. They combine those special properties we saw individually in both parallelograms and kites. And example 7 shows how you can use these diagonal properties to solve for unknown lengths within a rhombus.
Very cool. Okay, what other special parallelogram awaits us?
Next, we have the rectangle, and its definition is pretty straightforward. It's a parallelogram with all of its angles equal.
Okay, so we know all parallelograms have opposite sides parallel and equal, and opposite angles equal. What happens when we add the condition that all the angles in a parallelogram have to be the same?
Well, since the angles in any quadrilateral add up to 360 degrees, if all four angles in a rectangle are equal, each one must be 90 degrees.
Ah, so a rectangle is essentially a parallelogram with four right angles.
Exactly.
And because it's still a parallelogram, a rectangle also inherits those properties we talked about, like opposite sides being equal and diagonals bisecting each other.
Right. But rectangles also have their own special property when it comes to diagonals. They're always of equal length. The source uses congruent triangles to explain why this is the case.
Ah, so those two diagonals cutting across the rectangle, they're always the same length no matter what.
Exactly. And example 8 shows us how we can use that property to solve for unknown values related to those diagonal lengths.
Okay, we've explored the rhombus and the rectangle, both special types of parallelograms. What's left?
We've reached the pinnacle, the most special parallelogram of them all, the square.
The shape we all know and love. What makes it so special?
Well, the document defines a square as a rectangle that also has all of its sides equal in length.
So it takes the rectangle with its four right angles and adds the condition that all the sides have to be the same.
Precisely. But then it throws in this really interesting question in the think, discuss, and write section. Could we also define a square as a rhombus that has all of its angles equal?
Ooh, that's a good one. A rhombus already has all four sides equal. If we force all its angles to be equal too, what do we get?
Well, since the angles in any quadrilateral sum to 360 degrees, if all four angles in a rhombus are equal, they must each be 90 degrees.
Which means those angles are right angles, and we have a shape with 4 equal sides and 4 right angles.
That's a
So
square.
yes, a rhombus with equal angles is indeed a square. It's like we have two different paths leading to the same perfect shape.
Exactly. And that's the beauty of the square. It embodies all the key properties of a parallelogram, a rhombus, and a rectangle. It's like the ultimate quadrilateral overachiever.
I like that. The ultimate overachiever. So to sum it up, a square has opposite sides parallel and equal, opposite angles equal, diagonals that bisect each other like all parallelograms.
It also has all sides equal and diagonals that are perpendicular, like a rhombus.
And it has all angles equal and diagonals of equal length, like a rectangle.
So it's no surprise that the diagonals of a square have all those properties combined. They bisect each other, they're perpendicular to each other, and they're also equal in length. The paper folding activity in the document really brings all these characteristics together beautifully.
Okay, so the square is truly the VIP of the quadrilateral family. It has all the best features. But now, the document challenges our understanding with exercise 3.4.
This exercise is a fantastic way to test how well you've grasped the relationships between all these different types of quadrilaterals.
What kinds of questions does it ask?
Well, there are some true or false questions that really make you think, like, is it true that all rectangles are squares?
Hmm. Well, a rectangle has to have 4 right angles, but its sides don't have to be equal, whereas a square has both. So the answer is no, not all rectangles are squares.
Exactly. But is it true that all squares are rhombuses?
Well, a rhombus needs 4 equal sides, and a square definitely has that. So yes, all squares are rhombuses.
You got it. And there are questions that ask you to identify quadrilaterals based on specific properties they give you. Like, if a quadrilateral has all sides equal and diagonals that are perpendicular bisectors, what is it?
A rhombus.
Right. And importantly, you're asked to explain why a square fits the definitions of all these other shapes. A quadrilateral, a parallelogram, a rhombus, and a rectangle.
So you have to really articulate your understanding.
Precisely. And there's even a section where you have to name quadrilaterals based only on descriptions of their diagonal properties.
That sounds challenging.
It is. And then, of course, there are those think, discuss, and write questions that really encourage you to delve even deeper into these definitions and how they're all interconnected. It's not just about memorizing facts, it's about really understanding the concepts.
So as we wrap up our deep dive today, we've covered a lot of ground.
We started with the fundamental definition of a polygon and then really dissected the different types of quadrilaterals.
We went from the foundational trapezium to the unique kite to the versatile parallelogram, and then to those highly specialized parallelograms. The rhombus, the rectangle, and of course the one and only square.
Hopefully you, our learner, now have a much clearer understanding of what defines each of these shapes and how they all relate within this fascinating world of geometry.
We really hope this exploration has sparked some aha moments for you, revealing that there's more to these shapes than meets the eye. It's not just about memorizing names and properties, it's about understanding the elegant logic behind how these shapes work.
And to leave you with a final thought to ponder, we've seen how quadrilaterals are categorized in a sort of hierarchy, where a square is a special type of rectangle, but a rectangle isn't always a square. Think about this. What other systems of classification in the world around you follow similar nested patterns of increasingly specific criteria? How does understanding these kinds of relationships, where one thing is a specific type of another, help us organize information and see the bigger picture in other areas of knowledge? It's something to think about. Thanks for joining.